Thank you. Thank you very much for this nice, for this very nice introduction, Peter. I want to take some time, of course, to thank the organizers of this symposium for the invitation and for taking the time to show me around. Yesterday it was really nice, and I'm really happy to be here. And so we're going to kick off this day by planetary fluid dynamics. So we have a very diverse program, but we're going to start with some planetary science applied fluid dynamics. So in particular, I'm going to talk about the interplay between waves, zonal winds, and turbulence. So zonal winds are east-west winds, which are particularly well visible on gas giants, which is why we are going to focus on Jupiter today. So here you have footage of Jupiter's dynamics, in particular the dynamics in the cloud layer of Jupiter, which was taken by the Cassini probe. So you can see a very rich and very interesting dynamics, and in particular, you can see that this dynamics is chaotic and turbulent. In particular, if you compute the Reynolds number of this flow, which compares inertia to viscosity, I think I'm going to use the mouse, this is extremely large, and it tells you that the flow is turbulent. But at the same time, the Ekman number of the flow is extremely small because this is a huge planet which is rapidly rotating. So the flow is chaotic, but at the same time, it is constrained by rotation, as shown by the Rossby number of this flow, which is small. So this is what we call, this is a type of turbulence that we call geostrophic turbulence, and which is particularly difficult to study because of these extreme regime, extreme parameters in which they stand. This is an extremely chaotic flow, but at the same time, we have large-scale structures which are present and which are very long-lived. In particular, we have large-scale vortices. So you may know the famous Great Red Spot, but we also have more moderate white ovals, which are anticyclones. And we also have zonal winds, which will be the interest of the talk today, which are very fast east-west winds that are responsible for the banded appearance of the gas giants. And they are extremely stable since we observe them on the gas giants, which is pretty surprising given the turbulent nature of the flow. So they can reach velocities up to several hundreds of kilometers per hour. So they raise a lot of fundamental questions, both from the fundamental fluid dynamics perspective, but also from the planetary science perspective. I've listed key general questions here. How do they form? We don't really know if they emerge from shallow processes in the atmosphere of the gas giants, or if they originate from deep processes in the liquid interior of the gas giants. So that's a big question. How do they dissipate at depth, these zonal winds? What factors control their final intensity and also their meridional scale? Okay. What sets their long-term stability? Why are they so stable through time? And what is the feedback between these large-scale structures and the underlying chaotic turbulence and swirling motions that we see in this movie? So I was asked today to present you some experiments which were built at IRFE laboratory in Marseille while I was still in PhD there. So it was developed in collaboration with Benjamin Favier and Michael Lebars, and also Simon Cavan, who did a preliminary version of the experiment I will present, and Jonathan Ornu at UCLA, who initiated this experimental study. So before digging into more details, I just wanted to say that here I'm focusing on Jupiter because the jets are extremely striking on gas giants, but they are really ubiquitous features. You retrieve zonal flows in a lot of planetary flows, including the other gas giant Saturn, also the Earth atmosphere with the jet streams, the Earth oceans with, for instance, here the Antarctic Syncopolar current. They're also expected to emerge in brown dwarfs, or even in liquid outpores of terrestrial planets. So we have really fundamental physical effects which are present in all of these planetary systems, planetary flows, and this is why these are kind of ubiquitous features that we retrieve. So here is the outline of the presentation today. I will start with presenting this laboratory analog of gas giant zonal jets that was developed in Marseille laboratory. So if you want to build a laboratory analog of zonal jets, you need three fundamental ingredients. The first one that I already mentioned is rotation. Okay, we are dealing with rotationally constrained flow. If you have a rotating flow, the main effect is that, as you can see on this movie, is that it's going to constrain the motions to be invariant along the rotation axis. So this is the so-called Taylor-Prudman theorem. Basically, everything will be invariant, almost invariant along the rotation axis. This is important because it means typically that the flow will be quasi-bidimensional because you could describe everything on a single horizontal slice. The flow is quasi-2D when it's constrained by rotation. Why is it important? If you have a turbulent flow, which is three-dimensional, fully three-dimensional, the classical picture is to say, well, if I inject energy at some scale, it will cascade, we'll have a forward cascade towards smaller scale, larger wave numbers. On the other hand, if you have a quasi-2D or 2D flow, when you inject energy at some scale, it will be transferred towards larger scales. Okay, so we'll have an inverse cascade of energy. And this is a common mechanism which is invoked to say, oh, this is why we have large-scale vortices and large-scale structures on gas giants and also other rotationally constrained flows. So that's the first ingredient. We need the rotation. Second ingredient, we need what we call the beta effect. So usually the beta effect is defined as the variation of the Coriolis force due to rotation with latitude. I also like to introduce it as being just a topographic effect because it's a little bit more intuitive. So here on the left-hand side, I plotted a vertical cross-section of Jupiter, assuming that the dynamics is occurring in the spherical shell, okay? And I consider a fluid column with a given vorticity zeta, a given local rotation rate for this fluid column. If I displace this fluid column towards the north, I will squeeze it. And so the vorticity of this fluid column will decrease. Its rotation rate will decrease by conservation of, say, the local angular momentum of this fluid column, okay? And if I displace it towards the south, conversely, the fluid column will be stretched and I will increase its local rotation rate, okay? So if I have north-south motions in this kind of system, I will have sources and sinks of vorticity in the system. And this is an illustration of the beta effect. And you can see, most importantly, that it breaks the symmetry between the north-south and the east-west directions in the system. If you look at the equation describing the system, here I considered only the very simple 2D vorticity equations. The consequence of the beta effect is that it will add a new linear term in this equation, where the beta parameter depends on the variation of the fluid height, h, with cylindrical radius. So the fluid height measured parallel to the rotation axis. So here, just to illustrate the effect of this beta effect, I'm showing two DNS, direct numerical simulations of 2D turbulence, forced 2D turbulence, without a beta effect at the top and with a beta effect at the bottom. So if you have no beta effect, you have what I described earlier. You have a cascade, you're feeding energy into larger scales. Here you can see large scale vortices developing. When you add a beta effect, you also have the same type of process, but you see a very strong zonation that develops in the flow. And this is because of this anisotropy, which is due to the beta effect. And I don't know if you could see it, but you can also see on the simulations that you have westward propagating features. You can see that the flows, some features are propagating towards the left, which corresponds to the west direction. And these are called Rossby waves, okay, which is a new type of waves arising due to the presence of this term in the equation. I define two scales here, the transitional scale, which will be used in the following, which is basically the smallest scale at which your flow will become anisotropic. So it's when a turbulent turnover time equals a Rossby wave period. And the Rhine scale, which is thought to be commensurate with the typical scale of the zonation that appears in the system. So this is the large scale of the zonation. And finally, the third ingredient that you need is some forcing, okay, to trigger some motions in the fluid layer. So as I said earlier, on Jupiter, we don't know what is the nature of this forcing. It can be atmospheric processes such as moist convection, baroclinic instabilities, or it can also be deep convection in the deep liquid hydrogen of Jupiter. We really don't know what is necessarily feeding energy into the jets, what is the dominant physical process. And finally, experimentally, it's important to know what are in which regime you want to be. Okay, so I already mentioned this earlier. You need the Ekman number to be very small because you want the friction, the viscous friction, to be really small in your system. You want the Reynolds number to be high because you want the flow to be turbulent. And at the same time, you want the Rossby to be small. So you want the product of the Ekman with the Reynolds to be small because you want to be constrained by rotation. Okay. And there's a fourth dynamical constraint, which is visible through the zonostrophic parameter, R beta, which is the fact that you need the scale of the jets in your system to be large compared to the scale, to the transitional scale, okay, so to the smaller scale at which the beta effect becomes significant. So you can imagine that if you want to fulfill all of these constraints at the same time in a single setup, it's complicated, not only experimentally, also numerically, it's very complicated. So to illustrate this, I've represented here the gas giants and Earth atmospheres and oceans in a Reynolds Ekman space and zonostrophy index Reynolds space. And my key point here is just that gas giants are really in an extreme regime compared to Earth oceans, for instance. And the consequence of this, in terms of zonation of jets, is that the jets on the gas giants are much more clear. They are instantaneous features, very intense. They contain about 90% of the kinetic energy of the flow at the cloud level. Whereas in the Earth ocean, the jets are weak, meandering, and they are kind of latent features. You need some time averaging to reveal them. They're not instantaneous features. So our goal is to reach and study this kind of gas giants regime. I've added on these diagrams state-of-the-art 3D direct numerical simulations of gas giants dynamics, where they try to reproduce convective dynamics on gas giants. And you see that, so these are extremely costly simulations, and you see that they're barely, well, we're far away from being in the good planetary regime. And on the left, you have a 2D simulation, which takes advantage of the rotation. You can take advantage of the rotation and basically vertically integrate your equations to get a 2D model, which is much less expensive, but nevertheless, so it reaches more extreme regimes, but we're still not there yet, of course. And I've added the black dots here, which represent previous experimental studies. And what I want to say here is that there's been a lot of successes in reproducing zonal jets in experiments using various types of forcings. Nevertheless, the jets that were obtained are closer to an ocean-like regime, so weak jets, meandering jets, which are not very strong. The experimental setup that I built while I was still in Marseille, and that was studied previously in the previous version by Simon Caban, is able to reach more extreme regimes where we get closer to gas giants regime thanks to the fast rotation of a large cylindrical tank. So I'll present this in a minute. So this experimental setup was a cylindrical tank, as I said. It was 1 meter in diameter, 1.6 meter high. It was filled with about 600 liters of water and rotating at 75 rotations per minute, so more than a rotation per second. Because this is a fast rotation, what happens is that you have, because of the centrifugal effect, the fluid free surface becomes paraboloidal, just like when you stir your cup of coffee, okay, the fluid free surface becomes paraboloidal due to this centrifugal force. And this is very interesting for us because then the fluid height, h, increases with radius. And so we have a topographic beta effect because the fluid height changes with radius. You notice that the bottom of the tank is curved, and we did this because we wanted the beta effect to be uniform across the domain. So if you want the beta effect to be uniform, you don't need a parabola, you need an exponential increase of the fluid height with radius. Then, so we have rotation, beta effect, and then we need a forcing, which shows mechanical forcing, meaning that we have a bottom plate, which is drilled with 128 inlets and outlets, represented on the right. And we circulate the tank's water through the bottom plate, okay, by having submersible pumps placed beneath the bottom plate. We just do some kind of jacuzzi mechanical forcing at the bottom of the tank. This forcing is, the inlets and outlets are distributed on a polar lattice, but you can see that if you zonally average the forcing, it is 0 by construction, because we have as much inlets as outlets on each ring. So we are not directly pushing the zonal flow. Okay, if a zonal flow develops, it's an indirect process. Here, in terms of visualization, we added fluorescent particles and we do classical particle image velocimetry on a horizontal laser sheet crossing the tank at mid-height with a top view camera. So here you have a picture of the experiment when it was at rest. So you see the deep fluid layer, the cylindrical tank, the laser on the side, all the devices at the top, including the camera, and the bottom plate that you see here. And here I have pictures of the bottom plate with the curved, you can see it's curved aspect. And you can see when you turn it upside down, all the hoses and the submersible pumps that were placed beneath to kind of circulate the tank water through the bottom plate. So we had a great time plugging all of these 128 hoses to the bottom plate. Okay, and then here you have two videos. Once the experiment is in solid body rotation. So what you see very clearly on the left-hand side is the paraboloidal free surface, all right? And on the right-hand side, you see all the devices, including the camera and the desktop, which suffered a little bit from such rotation, which were all attached to the rotating frame. Okay, so let's switch to some visualizations of results. So here I'm showing the motions of the particles as seen by the top view camera. Once we have reached a quasi-steady state, so we have turned the forcing on and we have reached a quasi-steady state. So you can see that it's a bit difficult to see, but you can see that some zonal motions develop in the system, going either in the clockwise or in the anti-clockwise direction. So we are able to reproduce the spontaneous formation of zonal flows in this system. The surprise with the setup is that we identified two different regimes of zonal flows. So I'm going to illustrate these two regimes. On the left, I'm representing a space-time diagram of the zonal flow profile. And on the right, I play a movie of the azimuthal component of the velocity. This is regime 1, which is obtained at low forcing amplitude. So you see that there's a quick transient, and then we reach a quasi-steady state with narrow prograde and retrograde jets filling the whole system. Now, if we turn the forcing at higher amplitude, we switch to a second regime, which I call regime 2. And you can see its development of this movie, where you see that we start with regime 1, but eventually the jets will drift, merge, and you have a new statistically steady state where they are broader, they equilibrate at a broader scale, and they are much more intense. Okay. And you can see the corresponding space-time diagram here on the left with this long transient. So regime 1, regime 2. Now the question was, of course, why do we have this transition? And how is it triggered physically in the system? So we performed some hysteresis experiments where we changed the forcing amplitude step by step. And at each step, we waited for a new statistically steady state to be reached. And we measured the zonal flow amplitude. So here you can see the red curves. When we increase the forcing amplitude, there's a jump between regime 1 and regime 2 occurring at a given forcing amplitude, okay? If I do the same by decreasing the forcing amplitude, there's again a jump occurring at a lower forcing amplitude. So you can identify here a hysteresis loop, which means that the shaded area in the middle is a bistable range where you can either get regime 1 or regime 2, depending on the history of your system. Okay, so there's bistability associated with this transition. Okay, so now the question is, how do we model this transition and the associated bistability? So to model this transition, okay, what we do is, first of all, we are going to do a very simple 2D model of the experiment. Again, we take advantage of the fast rotation. We can describe everything on a 2D plane. Then we don't really care about the cylindrical geometry, okay? So we just work in an equivalent Cartesian system of coordinates, where X would be the zonal direction and Y would be the radial direction. So we have these very simple 2D equations, so which are the quasi-geostrophic equations. I won't go into this detail. And then what you do is you do a Reynolds decomposition of the flow. So you say that the flow is some zonal average, so along X plus a fluctuation, this should be V, a fluctuation about this average. So U prime, V prime are fluctuations, and capital U is the zonal flow. You put this Reynolds decomposition into your equations, you zonally average them, and what you end up with is an equation for the evolution of the zonal flow. Okay, so this is classical techniques. And then you get in that very simple framework that the zonal flow U is dissipated in our modeling by some linear friction, which basically represents the Ekman pumping at the bottom of the tank, the friction at the bottom of the tank. And the source, the only source term for the zonal flow is so-called Reynolds stresses divergence. Okay, so U prime V prime are the Reynolds stresses. U prime V prime average zonally, and the whole term minus d by dy of U prime V prime are the Reynolds stresses divergence. So in a lot of studies of the dynamics, the long-term dynamics of zonal jets, if you want to understand these dynamics, what you need to understand is you need to model the Reynolds stresses divergence correctly. Okay, and in particular, you need to know how it depends on U and if there is a feedback of the zonal flow on the Reynolds stresses divergence. So to try to understand this, we looked at what happens at the very beginning of an experiment in regime 1. I just looking at just above the forcing ring, and this is the velocity pattern that I get. So on the left, you have, here on the top, you have the zonal velocity, and at the bottom, the radial velocity. Okay, and you see that we have this westward, so the left is the west again, westward going pattern. Now, what I did is that I took the Rossby waves equations. Remember, Rossby waves are these waves which exist due to the presence of the beta effect, so those vorticity waves. I took the Rossby waves equation, I forced it with a similar forcing as in the experiment. So I added some vorticity sources in this equation. So it's a forced dissipated equation, and then I search for the stationary solutions to this system. And I'm able to exactly reproduce the pattern that is obtained experimentally. So what it means is that what we see experimentally is really the radiation of Rossby waves into the system. Okay? So each forcing ring will radiate some Rossby wave in my tank. If you compute the Reynolds stresses divergence, so the source term, which is produced by such pattern, by the radiation of Rossby waves, you will get a prograde positive Reynolds stresses divergence at the location of the forcing, and a retrograde negative Reynolds stresses divergence where the waves are damped. Okay, so the picture is that each forcing ring radiates some waves. You have a prograde jet above each forcing ring, and you have retrograde flow in between each forcing ring. Now, this is the picture for regime 1, and the question was, okay, why do we have a transition to a second regime? And again, using a very simple 2D model, this quasi-geostrophic model, we're able to show that this is simply due to the resonance, the fact that these Rossby waves can become resonant due to the advection of the zonal flow, which affects the wave. So to illustrate this, again, I took my linear QG model. I computed the Reynolds stresses divergence amplitude as a function of the background zonal flow, U. And I found that it has this Lorentzian shape, which peaks when U, the zonal flow, is equal to the opposite of the phase speed of the wave. So what it means physically is just that, so it's just a linear resonance. If you have no zonal flow, U equals 0, your Rossby wave has a negative phase speed, it propagates to the west. And if you have a zonal flow which exactly cancels the phase speed of the wave, then the wave becomes stationary, it's phase locked with the forcing, and so it's amplified through time. So it's classical resonance, linear resonance mechanism. So I have this Lorentzian for the Reynolds stresses. Now we can look at the dynamical, go back to the dynamical system. I'm going to search for the stationary solutions to this system. So obtained when the forcing equilibrates this linear friction. And so I naturally will have 3 possible cases. So this is my friction, this is my forcing. I can be in a case where I have only a sub-resonant solution if the friction is high or if the forcing is low. And this would correspond to the first regime. If the forcing is high or the friction is low, I can have only a super-resonant solution, U2, and this would correspond to regime 2. And I can be in an intermediate case where I have 3 stationary solutions, one which is unstable, and so U1 and U2 are corresponds to the bistability, the regime 1 and regime 2, and shows that you can have bistability with this model. And quantitatively, if you look at the values, the amplitude of the zonal flow predicted for the sub-resonant and super-resonant solutions close to the transition, you get values which are consistent quantitatively with what was measured experimentally. So this means that this model shows us that, well, first of all, the transition that we observed is abrupt because of this bistability. And second, that it is triggered by a resonance of the Rossby waves that are emitted by forcing with due to the Doppler shift by the mean flow. All right, so this is the model for the transition. Now in this third part, I'm going to focus on regime 2 only. So the regime which is presumably the one which is closer to what we see on gas giants. So we're going to look at some spectral properties of the flow in regime 2. And why do we do this? It's because we have observables on Jupiter. So in particular, if you remember the movie at the very beginning, you could see the cloud motion. From these cloud motions, we're able to derive velocity fields of the motions in Jupiter's cloud layer. And from these velocity fields, some kinetic energy spectra were derived. So here we have the kinetic energy density as a function of the wave number, so decreasing scales towards the right. The dark blue curve in this spectrum, the dark blue spectrum is the spectrum of the zonal flow only. Okay, and the light blue one is what we call the residual spectrum. So it's the spectrum of all the fluctuations about this zonal flow. The first feature is that you have a scale, which is the transitional scale that I mentioned in the introduction, which distinguish two large scales where the zonal flow is dominant and small scales where the fluctuations are dominant energetically. So that's the first important feature. Then some quantitative predictions were made for the slopes and amplitudes of these spectra. So this is the so-called theory of zonostrophic turbulence. So for the residual spectra, it is predicted that we should retrieve a k to the minus 5/3 slope, which is consistent with an inverse cascade of energy. Okay, so this is the classical Kolmogorov-Pregnan bachelor k to the minus 5/3 slope. And for the zonal spectrum, it was predicted by Rines that it should follow a steeper k to the minus 5 slope, indicative of the interaction of Rossby waves. And the scale at which the two spectra intersect is, again, the transitional scale. So we can look at the spectra in our experiments and see if we retrieve similar features. So here on the right, I'm plotting some spectra obtained in an experiment in regime 2. And again, the dark blue curve is the zonal spectrum and the light blue one is the residual. So yeah, this is just a spectrum, a zonal spectrum during the transient. You see that initially it peaks around our forcing scale, Kf. And eventually, once we reached a quasi-steady state, we have more energy which has been transferred towards large scales. And this slope is consistent with a steep k to the minus 5 slope. Then you can see that the transitional scale sort of distinguishes here also the fact that fluctuations are dominant at small scales and zonal flow at large scales. However, you can see that it's difficult to argue for a clear k to the minus 5/3 slope on the residual spectrum. Okay, this is the gray. It's not very well visible, but this is the gray line. So the idea is that we just thought that this is maybe due to the fact that our forcing scale is really close to the transitional scale. And what it means physically is that as we force the flow is already anisotropic. So there is no space for an isotropic inverse cascade to develop between the forcing scale and the transitional scale. There's not enough scale separation between the forcing and the transitional scale. So just to test this hypothesis and be sure about what we're thinking, I just performed some additional quasi-geostrophic numerical simulations. So again, these are 2D simulations. We try to reproduce as much as possible the experiments on this bottom simulation by adding some vorticity sources as forcing in this QG model. And then I decreased the forcing scale here and here to see what it changes in terms of zonal flow pattern, amplitude, and on the spectra. So the first thing to say is, of course, that we were able to quantitatively reproduce what we would see in the experiment with QG simulations, which shows that a QG, a 2D model where we assume the flow to be quasi-2D and rotationally constrained is a good approximation. Then if you look at the spectrum, as you reduce the forcing scale, so these are the spectra from the QG simulations. The light green arrow shows you the forcing scale, which goes towards the right because we decrease it. And the yellow highlighted region is the region where we should have a k to the minus 5/3 slope. And you see that we are indeed able to retrieve this slope as we decrease the forcing scale and as we have a better scale separation between the forcing scale and the transitional scale. So this confirms the fact that the experiment is indeed in the good regime, in the zonostrophic regime, which is relevant to gas giants applications, which is limited by the fact that our forcing scale is too large. Okay, so I'm going now to finish this presentation by something a little bit more theoretical, analytical, which is how can we build a quasi-linear model to explain the equilibration scale of the jets in the second regime. So the idea is that the model, the first model that I presented, it was, I didn't say it explicitly, but yeah, I assumed the zonal flow to be uniform, okay, in space. It was just uniform zonal flow. I was just thinking about the amplitude of the zonal flow. So this model, by definition, cannot predict what is the scale of the jets, okay? Why are the jets coarsening through the transition? And this is presumably of interest because if this regime is relevant to gas giants, then we want to know what controls the scale of the jets in the second regime to better understand what controls the scale of the jets on Jupiter and Saturn. So the idea is that we're going again to work in the framework of wave mean flow interactions, okay? Still focusing on purely Rossby wave mean flow interactions and try to understand how we could model this. So again, same idea. I start off with the Reynolds decomposition. Again, in Cartesian coordinates, U is the zonal flow. U prime, V prime are the wave components, and I can derive a zonal flow evolution equation. Again, the goal of this modeling is to derive an expression for the Reynolds stresses due to the waves and express these Reynolds stresses as a function of U so that this equation is closed and I can just integrate it through time. Okay, the idea how we're going to do this is that we're going to explicitly solve for the Rossby wave fields by assuming that I have a given line of emission of Rossby waves. I will solve for the wave fields using a Wenzel-Kramers Brillouin approximation. And I will use this explicit expression for the wave field to compute the Reynolds stresses and plug it back into the zonal flow equation. This is inspired, for those of you who know this model, this is inspired by the Halton-Linsenplug model for the quasi-biennial oscillation. So it's an oscillation in the Earth atmosphere, and this is a similar approach. And I forgot to say that this is a quasi-linear approach where we neglect basically wave-wave interactions, and we only focus on the interaction between the zonal flow and the waves. So to try to understand this a little bit better, I'm starting off here with the Rossby wave equation in the absence of zonal flow and in the absence of dissipation. And it's just written with the stream function psi related to the velocity and vorticity. If you have no zonal flow, no dissipation, you can search for solutions to this equation under the form of unbounded plane waves. And then you will get the classical dispersion relation for the Rossby waves. And one important features of these waves is that the phase speed, the zonal phase speed of these waves, omega by k, is negative, meaning that these waves have a westward zonal phase speed. So here on this schematic, I just qualitatively represented the fact that I'm emitting waves at y equals 0, and I have a northward propagating wave and a southward propagating wave. Now I will add dissipation on top of this. So I'm just adding a linear damping. And why are we interested in dissipation? It's because as the waves dissipate, they will provide momentum to the zonal flow. So I'm interested in adding this effect because I'm interested in the exchange of momentum between the waves and the zonal flow. I have a damping rate R, and I can define an attenuation distance, lambda, which is the marginal group velocity of the waves divided by this damping rate. So my waves are dissipated over a typical distance, lambda. And finally, I'm adding a zonal flow, U, So again, I derive my Rossby wave equation by linearizing the system around this background zonal flow. And I assume that my zonal flow has an arbitrary meridional structure. You can see that it has two feedback effects in the wave equation. You have a Doppler shift, this term here, which is the advection of the wave. And you have the curvature of the zonal flow, which modifies the planetary beta effects. So these are the two important feedback effects of the zonal flow on the wave field. Then you can search for a solution to this equation using the WKB approximation. So just to give the physical idea, the physical assumptions that are underlying this approximation, you need basically the medium to be slowly varying compared to the wave properties. Okay, this is a little bit like the geometric optics approximation. Okay, so in our case, we need the zonal flow to be slowly varying in space and time compared to the waves. And we need to be in the weak damping limit, meaning that this damping distance lambda should be large compared to the meridional wave number of your waves. Okay, so you need the medium to be slowly varying so that you can locally find solution to your wave equation. Again, I don't go through the mathematical details. You can search for a solution by just saying that the stream function is some meridional structures times this complex exponential, and then the meridional structure is given by the following expression, again, obtained through the WKB approximation, and it involves L, which is some local meridional wave number, which is a complex number, where the complex part will represent the fact that the waves are damped, and you see that we retrieve the two feedback effects, so the Doppler shift and the curvature of the zonal flow, which modifies the background beta effect. So there's a possibly rich feedback effects and long-term dynamics occurring in the system. And from this from the stream function expression, you can derive the Reynolds stresses expression, and you obtain the following expressions. The Reynolds stresses are some amplitude times a decaying exponential, which decays over a typical distance, which is the attenuation distance. Okay, but this attenuation distance is modified by these feedback effects of the zonal flow. So to illustrate this and try to build a little bit more intuition, I'm just considering a case here where I have no zonal flow, u equals 0. This is my WKB wave field. Again, I emitted the wave at y equals 0. If u equals 0, then this integrand is 1. My Reynolds stresses are just f naught exponential minus y by lambda. So this is just a decaying exponential. So my Reynolds stresses, again, decaying exponential at the north and in the south direction too. I have a jump in the Reynolds stresses at y equals 0. I'm regularizing this jump over some typical distance delta y, which you can think as the forcing region. And if you compute the corresponding Reynolds stresses divergence, so the opposite of the y derivative, you get this curve, meaning that you have a prograde positive Reynolds stresses divergence where the waves are emitted, and retrograde acceleration where the waves are damped. And this is exactly, if you remember, what I mentioned at the beginning for the first model. You accelerate prograde jets where the waves are emitted. Now, just to illustrate the fact that we can have feedback effects, I'm considering a sinusoidal zonal flow, which is the dashed black curve here. And the zonal flow u reaches c, the phase speed of the wave, at y equals 1 and minus 3. And these are called critical layers when the zonal flow reaches the phase speed of the wave. And this is just to illustrate that the wave field is strongly affected by this, by the amplitude of the zonal flow. Typically, the waves are less damped in a prograde jet, positive here, and more rapidly damped in the retrograde flow. And there's nothing going through the critical layers. If you compute the Reynolds stresses divergence associated with this wave pattern, you will get, again, the following curve. So we still have this structure with the prograde jet at the prograde acceleration at y equals 0, retrograde acceleration on the flanks. However, you see very clearly, well, the feedback effects of this background zonal flow, which modifies the behavior, the shape of these retrograde accelerations. Okay, so we have this expression for our Reynolds stresses. it only depends on U, the zonal flow, and parameters of the system. So we can put it back in the zonal flow evolution equation. I have a closed equation for U. I can integrate this equation through time, and I'm doing so here just by assuming, by taking periodic boundary conditions in Y. The key point is that I want to understand why we have locally driven jets here and globally driven jets here. So what I'm doing is that I will not only emit one wave, but I will emit several lines. I will emit Rossby waves at several lines of emission in the system and see what happens. So I made the problem dimensionless, but I see that I'm short on time already, so I will skip this. But it's not a big problem anyway, because I didn't have the time to do the parameter survey yet. So these are just two cases at fixed parameters. The first case on the left is a case where the emission latitudes of the waves are separated by 1.2 attenuation distance. And on the right, the emission latitudes are separated by 0.4 attenuation distance. So here you see the evolution of the zonal flow through time. So that's the first case. My emission latitudes are kind of far away from each other. Each line of emission of Rossby waves will trigger prograde jets where the waves are emitted. Okay. Now the second case on the right, I emit, again, the waves are emitted closer together, separated by 0.4 separation distance. You see that we start with these individual jets. And after some time, there's an instability that grows on this steady state. And we end up with a new system where the jets have a different amplitude and a different scale. Okay, so this shows that I can have interesting, again, these are very preliminary results, but it's some kind of proof of concept that this kind of very simple quasi-linear model, where we neglect complex nonlinear interactions, can explain some interesting features of the zonal flows over long time scales. Okay, so I'm going now to conclude my presentation. So I presented in the first part an experimental setup where we are able to reach extreme regimes of zonal jets. I added even with bottom friction because numerically it has been a challenge to, in global 3D spherical shell simulations, it has been a challenge to obtain jets with a no-slip bottom boundary conditions. And experimentally, we show that it shouldn't be a problem. It's just that probably viscous friction is too high in these models. Second, I really want to insist, but I think I mentioned Rossby waves so many times in the talk that you understood that I think Rossby waves play a key role in the dynamics of the zonal flow. And the feedback of the zonal flow on the Rossby waves dynamics is crucial to understand the long-term dynamics of the zonal flow. So here, for instance, the bistability and the transition between locally forced and globally forced zonal jets. I won't say that there are lots of very interesting dynamics, fluid dynamics occurring on gas giants that I did not mention. Typically, it would be very interesting to study further the interaction between those large-scale vortices and the zonal jets. Also, Juno, the Juno mission revealed very interesting dynamics at the poles of Jupiter. In particular, I don't know if you have seen these pictures of clusters of circumpolar cyclones surrounding the North Pole and the South Pole of Jupiter, which are, I think, very interesting from a fluid dynamics perspective. And also, Juno showed that the jets, I did not mention it, but the jets that we see extend over several thousands of kilometers inside of Jupiter. Okay, so they're down to a depth of about 3,000 kilometers for Jupiter. Whereas the jets are, the vortices, are shallower structures, which are of about 100 kilometers deep and a bit shallower for other vortices. So the jets extend deep beneath the atmosphere of Jupiter, and we also have some shallow structures in the atmosphere. So one study of interest, I think, is to understand how those barotropic zonal jets could interact with a shallow stratified layer, and if it can trigger vortices, and what is the interaction with these vortices, and so on. Okay, thank you very much for your attention, and I will be glad to take any questions. Thank you.